My goal is to understand the code that the Odin compiler generates. Ultimately, I want to have a gut feel for the difference between new and make. I'm going to start small and build up. First, let's have a look at the register layout for an x86 CPU. I see 4 general purpose registers, A, B, C, and D. They're called RAX, RBX, RCX, RDX. I see a stack pointer register called RSP. The stack pointer points into RAM starting at the high end and moving towards 0. Here's the instruction pointer, register IP, and a set of flags that the CPU sets. I'm not yet sure what all these other registers are. We can just ignore them for now and incrementally learn what they are used for as we examine more code snippets. Here, I've created a small function called PT. I avoid main for now because main usually contains code to set things up, and I'm not interested in such details yet. Also, I avoid constants, since compilers try to be smart about them and calculate them at compile time, and fold them into smaller, less obvious code sequences. So I've created a function that accepts 2 parameters and produces 1 result. In this case, I'm using ints, hoping that this will generate straightforward code. The function simply adds the 2 parameters together and returns the result. Here's the makefile for compiling the simple function. In Odin, all code is in packages, and packages are in directories. We simply need to ask the Odin compiler to compile all of the Odin files in this directory. Now I switch to the shell while splitting the window to show the source code and the shell. I compile everything using make. Then I run the debugger LLDB. I set a breakpoint on my test function. Using Odin, the name of the function is prefixed with its package name, in this case Odin ASM. I run the code and it stops on the breakpoint. I disassemble the code at this point. We see that the parameter x comes in the RDI register and is stored on the stack in location 0x8 down from the stack pointer RSP. Y comes in the RSI register and is stored 16 bytes down from the stack pointer. The numbers we see are prefixed by 0x, which means they are expressed in hexadecimal. 0x10 in hex is the same as 16 in decimal. Then the function header jumps to the function body, which in this case is the next instruction. The code loads parameter x into the A register and parameter y into the C register from their saved locations relative to the stack pointer. The x suffix in register names like RAX probably means extended. This is probably due to historical reasons. CPUs started out being byte-oriented, then were extended to be 2-byte, 16-bit oriented. This is probably when the x suffix was invented. Later, the extensions were further extended to 4-byte orientation and so on, but the x name was kept for backwards compatibility. I see that the function's return value is stored in register RAX. In this case, the value of the y parameter is simply added into the RAX register, which already holds the value of the x parameter. Yes, we're seeing decades of deep thought here. The algorithms in the compiler sort things out so that certain values are in certain locations that make the final code more efficient. And finally, now that the result has been calculated and left in the appropriate register, the code simply executes a return instruction. And here's where the code repo and the register diagram that I used are.